Well, good afternoon, everyone, and welcome to our Wednesday Virtual Connects. We're glad to have you here, and we're especially interested in learning more about health, safety, and welfare requirements for continuing education. And this topic is one that was of high interest to our members before we went to the stay-at-home order and things changed, and we hope it's still of interest to you today. And so we're continuing our series with alternative means and methods, including mass timber. We're excited to offer this opportunity, and we are allowing you to have some interaction as well. We invite you to use the Q&A feature, which you can see on the bottom of your screen in the Zoom viewer. As you populate those Q&A questions, we'll get to those at the end after we wrap up the presentation and try and answer as many as we can. If you stick around for the whole hour, we will offer you an HSW credit, and we'll give you instructions at the end on how to get that recorded properly. So today we're very pleased to have Code Unlimited as our presenter. They provide a wide variety of code consulting services to the architecture and engineering community, as well as local authorities. Code Unlimited has 4 locations, including an office here in Lakewood, Colorado, and are silver level industry partners to AI Colorado, and we're grateful for that. Our presenter is Samir Mokashi. He's the founding principal and owner with over 30 years of experience in regulatory requirements. He successfully led design teams through highly demanding programs, complex designs, challenging budgets, fast-track schedules, and rigorous requirements. And now you'll have something else for your bio, Samir, leading your consulting teams through pandemics. Having worked throughout the US, Europe, Asia, and Middle East and on projects large and small, it gives clients the advantage of deep experience. Samir's been involved in code development at the local and national levels and authored several code alternatives and variances that resolve multidisciplinary issues, both simply and effectively. So Samir, we are grateful for your depth of knowledge that you're sharing with our members today and invite you to take it away.
Thank you very much. So good morning, everybody, or good afternoon for you guys. I'm 1 hour behind you guys. So I'm going to share my screen in so hopefully everybody can see my screen, and we'll start from there. So this is a unique presentation that I custom designed for the AI Colorado. I've given similar talks to other jurisdictions, but this is custom fit to your needs and your requirements. So we'll talk about that. So in this particular presentation, we're looking at wood, especially mass timber, and talk about that. And then we're going to talk about alternates to the prescriptive code requirements. And we work with a lot of architects, engineers, and owners developing the alternates. Sometimes the alternate is because you got in a jam by following something that the jurisdiction says does not work, or the code has changed or something like that. And we develop an alternative that is equal or better. And sometimes it's your creativity. You're developing a design and pushing the boundaries of the design that doesn't fit very well in the code framework that is designed for one size fits all. So with that, we'll kind of go with a couple of requirements for HSW credits. So we're going to talk about wood construction and performance alternatives. The AIA Colorado will do the continuing education credits, and it's registered for 1 hour HSW. Tim just talked about me and what I do, so we'll skip this slide. The learning objectives is we'll give you an overview of type 3, type 4, and type wood construction. And then CLT is cross-laminated timber. It's a subset of mass timber. And type 4A, 4B, and 4C construction are the construction types that are coming. This is approved to the 2021 ICC code change. So it is not even in the 2018 code, but it's adopted upfront by many jurisdictions, including Colorado. Oregon and Washington, Oregon has adopted it into our codes that we adopted in 2019. Washington has adopted it as a separate add-on amendment to the code, and I'm not certain how Colorado is doing it. But either way, this is becoming more prevalent. More states are coming on board and doing it. So we'll understand the code intent and how to isolate code sections to develop code alternates. So when you're writing a code alternate, there's a specific framework and a method to it. I'll talk about it as I go and talk about the different alternates that we have done. We'll also talk about engineering judgments. So engineering judgments are where there's no tested assembly or listed assembly, and we develop an assembly that will work for your buildings. So we'll talk about both performance alternatives as well as analytical empirical alternatives that we've done. And then just some of the case studies that we talk about are out-of-the-box design solutions. The client comes to us and say, can I do this? And we're kind of like, maybe. Let me ask you a few questions and see where we end, and then we can develop an alternative. For most cases, we are able to develop a pretty good alternative that fits the design goals. We try to make it simple. We try not to make it overly complicated because safety is the ultimate goal, right? So if you make a very complicated alternative that takes very difficult to install or very difficult to maintain, then we have not achieved the safety intent. So that's also something to keep in mind. So we'll start with the wood construction types and get into mass timber and talk about that. So wood construction type, amongst them, the type 3 is the least understood construction type in working with different architects and jurisdictions and things like that. I find a lot of kind of a spec office, spec warehouse buildings that are 2-story with 60-foot yards, often listed as type 5E. And we look into the details and we find that they're actually type 3 construction and not type 5. In a type 3 construction, there are a couple of critical things. One is the exterior walls are non-combustible, or they're fire retardant treated wood if the wall is 2 hours or less. And the interior elements are any material permitted by this code. So any material permitted by this code means you can have wood, steel, anything, right? So even though these are typically wood buildings, it allows you, you're permitted to have non-combustible steel framing within it. The wood becomes the lowest common denominator. And in this one, if you look at the lower left picture, the exterior wall is a masonry wall. On the top left, it's a precast concrete tilt-up panel, and the roof framing is wood. In the middle picture, you can see that there is some heavy timber members, there's some regular wood framing, so it's a combination of pieces as well. So type 3 could have multiple elements in it that you typically consider wood, but it could also include non-combustible elements. But the exterior wall has to be non-combustible or fire retardant treated. So type 4 construction, on the other hand, is very similar to type 3, but it's not frequently used. And the reason it is not frequently used is because of its restriction on concealed spaces. In most facilities, if you have a drop ceiling or something like that, you would have a concealed space. And type 4 construction does not allow it. Type 4 evolved after the Chicago fire when there was a lot of warehouses and storage places which had heavy timber construction. And when the fire started, it just spread from building to building to building. So a couple of things in that, it's that the interior is heavy timber and the exterior, again, is non-combustible construction. And when you have heavy timber construction, heavy timber is defined by the size of the solid wood, but it also allows you to have solid wood, you have glue laminated wood, structural composite lumber, or cross-laminated timber as part of the type 4 construction within the 2015 and 2018 codes. So in the in that code, this table kind of summarizes, if you have a solid sawn, in the left 2 columns is the width and depth of the sizes that you require, then the glue laminated dimensions are different and structure composite is different. And that's based on just the performance of the different members and how they're available, either nominal or actual dimensions and things like that. And so the dimensions that are given are the actual dimensions of those wood pieces. Here's an example of heavy timber. You've seen the log cabin type of construction, that is heavy timber. You've also seen some CLT uses, and that also can be part of the heavy timber. And then 2021 creates a separate CLT construction type, and we'll go into that in details as well. Type 5 is the lowest construction type that you can build out of. Again, type 5 is typically understood to be wood construction, framed wood construction, but you can have plastic for that matter as an element. You can have steel as part of that construction type, but the type 5 is typically the lowest construction type. So your typically areas, number of stories are all limited, and that's based on just the risk assessment and risk management of the code. The lumber sizes, the nominal number versus actual dimensions, the table on the left is some architects work a lot more in wood, others don't work in wood, and so understanding what you're seeing and what your code is requiring is important. So again, type 5 is anything in the wood, typically wood framed, does not have a restriction on the exterior walls like type 3 and 4 have. Type 3 and 4 both require the exterior walls to be non-combustible or fire retardant treated. Type 5 allows you any construction type. In these construction types, there is a type 5 and type 5A. Type 5A is typically 1 hour construction. Type 5 is B is non-rated construction. Similarly, type 3A, type 3B. Type 3A is 1 hour construction. Type 3B is non-rated construction. Type 4 is just type 4. Eventually, type 4 with the CLT becomes type 4 HT for heavy timber. So let's talk a little bit about mass timber and how mass timber is defined, how it works. So the mass timber is the umbrella term, and under that you have CLT, cross-laminated timber. You have NLT, nail laminated timber. You have DLT, double laminated timber. You have glue laminated timber. And also parallel strand lumber. All of these are subsets of the mass timber. So cross-laminated timber is prefabricated engineered wood product, not less than 3 layers of solid lumber, and they're placed in cross directions. One goes one way, the next layer goes the opposite direction, and the third goes back again. So in a way, it is like a two-way slab, reinforced two-way slab, or reinforcement going both directions. And that is the advantage of cross-laminated timber, because the timber strands or timber members go in 2 directions, it has strengths in both directions. Typically, I mean, 3-ply, 3 layers, 3 lam or 5 lam or 7 lam. We've seen some larger ones, but the 5 lam is the most common that we've seen. 3 lam is typically not fire rated, and 5 lam is fire rated, 7 lam is fire rated is typically how we find out. So panel thicknesses could be up to 15 inches. The 5 lam is about 6, 7, 8 inch thick. And the width of the panel can go from 2 foot to 12 foot, 20 foot to 60 foot long. These dimensions are really driven by the manufacturer's equipment and how much, how large an equipment they have, what type of capacity they have, and that actually helps define the element of this. So understanding mass timber and how it works. So one of the common things that come up with everybody is that wood is combustible. So if you're building a cross-laminated timber building, you're essentially creating a pile of wood that can be ignited by a matchstick, and it will all go up in flames. So let's get a little bit into the details of the material qualities and material properties and how they're different. So commonly, most commonly, fire marshals and also others that we talk to come back and say, oh, steel is the best element because it's non-combustible, it will not burn. And wood is the worst element because it will burn right away. Well, it's not that simple. There's a little nuanced understanding to it. One, steel, even though it's non-combustible, is typically not where the fire starts. The fire starts with the contents of the building, not necessarily at the structural component of the building. 2, the failure of the material is also significant because what we see as fire is we see it as flames, as ignition, but really in terms of thermodynamics, the fire is just elevated temperature. flame is in one expression of the fire temperature, elevated temperature is the other, much more significant impact on the structural elements. So steel, when it's exposed to temperatures over 1300 degrees Fahrenheit, it fails. So it becomes so malleable, it cannot hold its weight and it falls. So typically we protect steel by sprayed fireproofing or an envelope around it. And so that envelope is providing insulation to prevent the temperature from outside that envelope to protect the steel inside. So the surface temperature of the steel is not allowed to go over its failure temperature. This is how fireproofing works in steel. Wood works where CLT works very similarly. In this diagram, if you look at the white dashed line, that's the size of the wood member needed for the structural stability of the building. And then the black dashed line is the size of the member that is used to design the building. So the space between the white dashed line and the black dashed line is the insulating element. So the fire attacks the outside and burns through, and until it burns through the white line, the temperature inside is not reaching to the fire temperature. Another thing that is significant in wood is wood failure occurs by mass loss. Wood can handle a lot of temperature. So the wood member can go up to 2000 degrees and not fail. It fails when you burn through. So a steel can get exposed to elevated temperature and fail right there at that temperature. For wood to fail, it has to burn through. And as the wood burns through, the charring that takes place actually protects a barrier for the fire to progress, because the char acts as insulating material, and char also displaces oxygen, so it starves the fire. So the CLT members are not necessarily performing worse than steel. They're performing differently than steel. So in the CLT, there is a type 4A, type 4B, and type 4C, the three different construction types, and they're introduced in the new code, or will be introduced in the new code, and some jurisdictions have adopted them early. So type 4A is loosely based on 18-story Brock Commons. It was done by Acton Ostry Architects in Vancouver, BC. So the code team looked at existing buildings that had used mass timber, followed up on the research that was based on mass timber, but this is where it comes from. So the 18-story number comes from that building example. Then the type 4B is loosely based on a 12-story framework building built here, or rather designed here in Lever Architecture. It was not fully finished because the funding went away, but the building was designed, it got its all approval through the local jurisdiction. And that again is a 12-story office building. If you look back at the code, you will notice that this is 12-story office building is also comparable to type 1B construction and what is permitted under that. Then 8-story carbon 12 building is the one that was used to develop the type 4C construction. This was in Portland by Kaiser and Path Architecture, and that is the basis for it. So if you look at the type 4A, B, and C construction types, this is kind of the cheat sheet of what you need to know if you're starting up into it. There's a little bit more to it, but here's what you start out with. So type 4C and type 4B, in both instances, the primary structure is 2-hour rated and exterior bearing walls are 2-hour rated. In type 4A, the primary structure and exterior bearing walls are 3-hour rated. One of the things is that in all three construction types, the exterior wall face has to have a chipboard on it. And then the interior wood, there is a variation whether it's permitted to be exposed or not permitted to be exposed. So in type 4C, the interior wood, framing, exterior walls, floors, everything can be exposed, and that is permitted. In type 4A, nothing is exposed, everything is covered up. And type 4B is the in-between, that is neither A nor B, and is the most problematic area that we're finding right now. One of the things that is happening is for most architects, they want to design to type 4B, but they don't want the restrictions on the exposed wood. And we'll talk a little bit more about some of the designs that we're working on where this condition exactly happens. So in the type 4B, you're allowed 20% ceiling or 40% of wall to be relative to the floor area. So if the floor area is 100 square foot, you can only have 20 square foot of ceiling exposed. If the floor area is 100 square foot, you can only have 40 square foot of exterior wall exposed. So that is the conditions. Now, if you look at the allowable area and heights, you will see that type 4, type 3, difference between type 4E and B, in the, there's a screen here that is blocking my path. I'll take that and put it on the side. Okay, so in type 3B, the building height is 75 feet. Type 4 heavy timber, or type 3A under the current codes, is allowed 85 feet. So type 4C starts with 85 feet, type 4B go to 180 feet, and type 4A goes to 270. So it's pretty tall structures that are permitted under wood. So the advantage of the CLT is it's lightweight. Typically, steel and concrete structures get very heavy because your floor is always a composite deck, which carries a lot of weight as the stories go up, and wood is much lighter than that, and there's savings there. Also, the wood comes in pre-prepped, so you don't assemble or frame on site. You come a manufactured piece, and the installation goes much faster than traditional building construction. A couple of things to watch out for is in different occupancies like an I2 or an I3, there's different permissible heights and stories than what is permitted in other cases. One of the things that comes up is wood joinery in CLT. Because wood CLT is fire rated, the joinery is very important. In some of the early CLT manufacturing, the joinery was exposed, and we had to design fire ratings or fire rated protection for those joints. Now, a lot of the material is doing concealed fasteners, like you see on the right, and the beam just slides right into it, and the fit is really, really tight. You don't get that kind of construction finish and accuracy, even in the steel structures. So the finished product of CLT is very, very accurate, and much more so than steel framing that we are used to. And what you do is typically you have a fine fire caulk continuous bead applied around the joint, and that gives you the fire rating because the steel is not exposed, and the fire caulking, intermittent fire caulking, protects the joint from fire. Many of the assemblies are now tested for fire, and so you have a listed assembly, but if not, we can create engineering judgments for those. This is a condition where there's a wood column supported on steel plates, and then what happens is the concrete fills up and covers up the steel plate, and that's how fire rating is achieved at the floor level when you have connections at the wood. There's also a lot of through penetration joint protection is now available. There's some tested assemblies. Some of the things to think about is when the joint, in typically steel or concrete assembly, when the penetrating element is exposed to fire, what happens is that the penetrating element is the only thing that is affected by fire, and rest of the structure is not. But in wood, when the fire also affects the wood, and as the wood gets burnt along the penetrating item, that condition is different than typically a concrete deck or a steel deck. So the penetration assemblies are different for CLT than what they are for steel or concrete members. So now we'll go into alternate materials and methods. So there's two things in the code. One is called a code modification, and then the second one is called alternate materials and methods of construction and equipment. So the code modification is really a waiver. So this one says that if you cannot meet the code, you write a code modification to the jurisdiction and ask for a waiver that because of this, you cannot do it. Typically, it happens and says you have an existing condition that you cannot rectify is where you'll go for a code modification. The code alternate, on the other hand, is saying that I don't want to meet the prescriptive criteria the code says, but I will provide equal or better protection with a different assembly or method of construction. Both are permitted by the code. The alternate materials is the more common one because the jurisdiction is not waiving the requirements, but requiring you to meet them differently. And when this condition happens, typically the key issue in that becomes that the onus is on the designer and the code consultants oftentimes working with you to develop the alternative and do it. So one of the things is also establishing what was the code intent behind it and then meeting that requirement. So in CLT or heavy timber, there are standards that are established that allow you to calculate the fire resistance of the building element. So based on the thickness of the wood, based on and we work with the structural engineer to understand how much of the wood is going to be a structural component and how much beyond that is for fire rating. And we can develop alternatives based on that. We typically have an engineering judgment that is stamped by a fire protection engineer is the deliverable and the final result that goes to you and to the jurisdiction. I talked to you about the CLT systems in prior to the concealed fasteners, or even today, there's some architects like to see exposed fasteners and things like that. And especially if it's a fire rated component of that element that needs to be protected. So we had two options. In option left, we used intumescent. So we look at the steel plating, compare that to established testing on similar materials or comparable materials, and then extrapolate from that what would be needed for the steel material to be protected by intumescent material. So intumescent would get applied on that. On the right-hand side, we actually used wood, sacrificial wood. So wood is applied on top of the joint. That wood is not part of the structural element. It is just applied like a sprayed fireproofing on top of the joint to protect the fire from eating through and attacking the steel connecting members. Here's an example where it was a hybrid system. And this is not uncommon in CLT because CLT performs really well, but it's very rigid frame. And so sometimes steel is used at the core elements for cross bracing and things like that to manage the lateral seismic conditions better. So in this instance, the steel was connected to CLT. It was in the middle of the shaft, the core of the building. And so the steel was protected by sprayed fireproofing. And our fire protection engineers looked at it and actually required that the sprayed fireproofing extend a certain distance out from the steel onto the wood in order to provide the protection that the steel needs at the joint and transition from steel to wood. So this becomes like a case-by-case analysis, but this is typically at the shaft inside the building. So the gypsum board was covering it all. So we did it with sprayed fireproofing and made sure the fireproofing could adhere to it properly and do it. We can do it with intumescent, we can do it with gypsum. So there's different ways to provide that rating, which it just gets a custom design at this level. Now we'll talk about some wood, concrete, and steel framing and how do you do fireproofing for that. So here was a condition where there was a corridor ceiling, floor ceiling assembly that was done by just 2x6 on an edge assembled, and in between the engineer added a HS tube framing member, and that was the one thing that was throwing everybody off and causing consternation for the designer and for the jurisdiction. They came to us asking for relief and say, can you look at this and tell us if it is meeting the requirement? So this was a 60-minute assembly required. So we looked at the wood framing and were able to determine that most of the wood framing was providing a 57-minute rating. And then we had tables that we were able to look at for the wood framing based on the type of the wood, And we were also able to look at the high-strain steel member and give it a rating of 10 minutes based on its dimension. And we were able to demonstrate that this assembly would withstand for 67-minute total. Together, the steel and wood were working in combination, and therefore we were able to establish that this was going to be at least a 60-minute rating. Another example was an existing building and the University of Oregon campus. It was a building that had a portion of the building was above it, portion of the building was underground, and there are multiple buildings forming a courtyard. And this under the courtyard was a building, and people walked over it. It was a complicated area. It was done in a period when there was a jurisdiction review was lax, and where one building started and one stopped was not very well established. We got into a lot of that and cleaned that up by being a podium style building. But now we required the basement underneath the courtyard to be separated by 3 hours. And it had a concrete waffle slab that was existing, and then top of that, the architect came in, put in insulation, rigid insulation, and poured a topping slab on top of it. So the original design did not have the topping slab. And so it was only a 3-inch waffle deck at the top, which wasn't getting the 3 hours that we needed. But with the topping slab, we were able to get that. We were also able to demonstrate that the rigid insulation, which was within the concrete, would stay stable at the temperatures, elevated temperatures, and would not be impacted and would not compromise the rating. So we looked at all of this and came back and established a 3-hour rating for that assembly. Here's another example that we're working on. This was a tube steel again, which was in an exterior wall assembly. The wall was framed, and then the tube steel was inserted to support it. And then the question was, how do you support it? And if you look at the details of it, the tube steel, the weight, the size of it, and the framing of it, the tube steel only had a single layer of gypsum, while the wall had 2 layers of gypsum. So the wall itself was 2-hour rated, and how do you handle it? Beam was the issue. So we looked at the beam, looked at the wall, looked at the assembly, and provided an engineering judgment that gave an intumescent coating thickness that can be poured on top of the tube, applied on top of the tube steel, and then the single layer of gypsum in combination with the intumescent fireproofing gave it the rating required for the wall. And we were able to do an engineering judgment again on that one. And for that one, we actually not only had to develop the tube steel, but we didn't find a beam assembly for it. So we looked at the column assembly and the intumescent for that, and then took that element, adjusted it for the beam performance. So the column and beam are under different loading conditions. So the requirements are different, the exposure is different. So we were able to translate that column information and apply it to a beam condition and provide an engineering judgment. So here's a couple of designs that I'm going to go into now. This is where we are using performance analysis rather than empirical analysis, and providing code alternative designs for that. So this is an interesting one. This is for a Multnomah County courthouse. The building is under construction, and it is now almost finishing. Will finish late this year or early next year, I forget. And this was interesting. The architect came to us early, and as part of the design concept, if you look at the picture, you see that grand entrance. That was a significant part of the experience of every person coming into that courtyard that the architect wanted to maintain. And so what that did is inside that structure where I'm showing was a 3-story entrance hall. And you would come in, it was like a procession. You would come into this building, take this stair up, go to 1 floor, go up 1 more floor to the 3rd floor. And when you go into the 3rd floor, you had a glass window that looked out into Mount Hood, a mountain in Oregon. It's a beautiful view, and so that was important part of it. But except it became a 3-story opening, and now it was an atrium. Since this is a courthouse, the people coming into this have to go through a very secured entrance and had to be controlled entrance going into it. And this was important issue that would be compromised if the fire started, smoke detected, and we were drawing air through the entrance doors. So the doors will be open and the security will be compromised. And so that was a concern. So in this one, we went to the city of Portland and we actually argued that this is a shaft, not an atrium, and we want to protect it like a shaft versus an atrium. And the difference between shaft and atrium, in an atrium, you could have multiple layers that are within the atrium where people could actually be using, working, doing activities. In a shaft, typically the higher levels of the shaft, nobody's there, and only people are there at the lower. For example, if you have a mechanical room and a shaft above it, people are accessing the lower level, but not the upper levels. And so we made that argument that the way this is designed, the upper members, there is no occupied levels that are exposed to this 3-story opening. And we also presented the logic that in an atrium, the separation is 1 hour and you have smoke control added on top of it, versus the shaft has 2-hour separation and no smoke control. The city accepted in principle, but they had some concerns. So one of the concerns was there was the fire, there is right here is the inmates were here and the police officers is all here as well. And this will be separate from that. So the building exits for these are directly into the stair at the top, so they didn't have to go through here. But under an emergency situation, they said, if there's a fire started and people started going here and there is a fire here, then what happens? So we actually modeled this and showed it to the jurisdiction. So we started a fire in that 3-story space, smoke detectors activate, doors shut down the 3-story. The stair is not a means of egress, so the stair doesn't need to be part of the egress. And because of the large volume of the space, there is a smoke reservoir that allowed the smoke to just collect up at the upper 2 levels, and the first floor was free for egress. And we demonstrated that. So there are a couple of things important. In this one, because this lobby was a public lobby, but not a lobby where people are sitting, there wasn't a large amount of seating or like a sofa or wood framing or wood furniture. So the combustible material content was limited and the volume was large. So that was the argument we presented. We also did an egress model. And if you look at this, the blue square is where you're going to see it. So the people in the main hall, which is the top left, kind of the triangular space that is there, is those people are going to see a fire start in this and respond to it. But the people in the rest of the building are not going to see the fire, are only going to respond after the smoke alarm detects it and that notifies them. So you can see the people on the left taking off. You see that little green dot where the circular template is? That's where the source of the fire. So the people in that have left. Security guards are making sure that the door remains locked and nobody's coming back in. And now the rest of the building recognizes this, and even though the exit stair is the exit, they don't need to go through. We also assumed that the people will be going through the other door in an emergency and not following the requirements, and therefore they're going through. And we considered that time, additional time for those people to exit the building as well in the model that I showed you just a little ago, the 3-dimensional model I showed you. So we were able to demonstrate that we don't need to have smoke control because of the size of the atrium that the smoke reservoir is maintained, people can safely egress that. Here's another example of using performance analysis. This is in Washington, Seattle. This was a high-rise building, and the occupant load at that floor went over 500 occupants and needed a third exit. Most commonly in these conditions, we typically recommend a horizontal exit, but Seattle does not like horizontal exits. So in this instance, we were fortunate. The stair on the left is stair 1, stair on the right is, stair on the left is stair 2, stair on the right is stair 1. Stair 1 was a larger width stair, so the egress capacity was large. As we looked at it closer, typically what we find is even in the wide stairs, the doors are narrow, and doors are the places actually that becomes a bottleneck in our analysis. So we proposed that we make that door wider to the stair, and we actually looked at the scenario of 3 stairs versus 2 stairs, and then did a performance analysis, went back to the jurisdiction, actually more people get down and faster in a 2-stair configuration versus a 3-stair configuration. So in the 2-stair configuration, exit time is 524 seconds. In a 3-stair, it became 562 seconds. So here's the 2-exit scenario. You'll notice that people have moved out of their spaces and they are now waiting in line to get down the stair because the door is the threshold. People get to the spot. So that's understanding that is important. And as we make wider doors, more people were able to get down that stair. So total time was 649 people exited and 584 seconds total for everything to go down. Here's the 3 exits criteria. And same number of people going through 3 stairs. In this scenario, because there is a stair, you'll find that people actually go back and forth when there is queuing happens. Some people go back and forth, and the analytical CFD model, the egress model that we use, is a very powerful modeling tool that actually allows us to assume those requirements. And here we find 649 seconds when everybody's left. So just by adding 3 stairs does not make the egress faster. So there is a different performance analysis that goes through. In this one, we had assumed everything was a 3-foot wide door. In the other one, we made one of the doors, I believe, 4-foot door, and that helped move people much faster. So there's kind of the things that we do, whereas the designer is developing something, and we work with the designer and the project goals to develop performance analysis that'll work well with it. Here's a condition that we had designed it as a 3-story open stair. This was when the first 2012 code edition came in, and the code actually permitted 3-story open stairs. And the way it was written, you could use it as a means of exit, as an exit access stair. And then later on, we submitted this for an appeal in City of Portland, got it approved, and then somebody went to a code seminar and they found out that there was an obscure requirement in 2012 that said you can only go down 1 floor and not all the way down. So this that was approved came back. So now we were stuck because the design was quite a ways through. Fortunately, again, this stair was a 6-foot wide stair. So it's a much wider stair because it was a central stair. It was not limited to the size because it was a grand stair. And the code restriction on not allowing people to go down more than 1 floor is based on travel speeds. The people travel faster on horizontal surfaces and they travel slower on the stairs in going down. And so therefore the code allows you to use travel distance, exit access travel distance, as if it is a horizontal surface, and does not account for the slower speed. Except on a stair, when you're walking through, you're much closer to each other. On a corridor, you will not walk as close to each other as you would walk down the stairs. So the rate of flow of people on a stair, even though overall slower, is higher than what's on a corridor because more people are going through per square foot. And we did calculations based on that and came back to the city and demonstrated that in this building, by using this 6-foot stair versus a standard 3-foot stair, that the people going down would actually be delayed only by 5.84 seconds compared to what they would be doing if they went down just the standard stairs. And the city looked at it and reapproved that approach, which they had approved previously, then denied, and then got reapproved. So here's the challenges that happen. Here's on the condition. This was an existing student union building in University of Oregon that was built as a Type 1B building. And then the architect came in and wanted to redesign an addition to the building. And because it is Oregon and wood is such a common element, and University of Oregon is heavily involved in CLT development as well, they wanted to build out of heavy timber components. We told the architect that will be very problematic, don't do that. Of course, they didn't listen to us. So we had to come back and develop an alternative. So what we said is what we did is we developed a firewall between the Type 1B and Type 4 construction between the two, except part of it was existing. We didn't have a full firewall, prescriptive firewall built. Parts of it had very large openings that in it. So we had to develop a strategy that covered up, addressed all of them. So here's the firewall that is there right now. So right there behind the 3 girls walking is the firewall that we have designed. As you can see, you don't notice the firewall at all. But what is all built up is there is a shutter that closes off here, and there is different sprinkler designs there and here, and there's rated walls in between as you go further back. So we did a combination of a 3-hour firewall was existing, 3-hour fire barrier wall where we couldn't made it exactly, and then we added extra sprinklers on either side of it. And especially on this side of the 3-story open space, we had large drop sprinklers figured out. So our fire protection engineers, our building construction experts, in all of it, we worked together with the architects to develop a scenario that will work with the design and meet the code requirement. And the city of Eugene was great to work with, but they were not cutting us any slack because for the firewall, they wanted to make sure that everything would work very well. So we worked very diligently. This was reviewed with the fire marshal, with the building official, and then got approved. Here's another requirement. This was a unique one. The building was a standard residential building. At the lobby, there was an art piece. This art piece was the thick ropes hanging from the ceiling and had a wavy structure. It looked beautiful. The fire marshal walked in and said, my sprinklers are obstructed. I'm not going to permit this. Take down the ropes. My sprinklers need to be able to work as designed. We got a late call late in the evenings. Our fire protection engineers looked at it and said, yep, you have a problem. What we did do, we actually developed a solution. What we did, a combination of the ceiling pendants and upright sprinklers at a lower level. We did 2 levels of sprinklers. So the lower sprinkler actually could activate earlier, as if the fire starts and the fire is starting and the heat is accumulating here, there was a heat collector. So the lower sprinkler will activate quicker. And then as the fire progressed, the higher upper sprinkler would progress as well. And the fire marshal accepted this answer. And we were able to get the project back on track and open on time. Here's another one. This is at the Oregon State University. This is again a student union building. In this case, there is a stair at the top right and stair at the bottom left. Both enclosed stairs are straight exit stairs. In the middle was a 3-story structure with open stairs coming down. You can see this slightly in the picture on the right. So we went in and made the argument that the exit stairs are not, exit is not required to go through the stairs. It is like an open exit access stair. And we put sprinklers and draft curtains along this way, so there will be protection from here. We also had added kind of a smoke fan at the 3rd floor level. This is a 4-story building, but there was a rated separation at the 3rd floor. There was a fan added at the top that would exhaust excess smoke as well. So we thought we had a pretty solid case for this being done. then the jurisdiction changed personnel. And the person who had plan reviewer who had approved this left and a new plan reviewer came in. And unfortunately for us, that plan reviewer did not agree with the previous and reopened the case. So we were able to show him that, look, we have this protection and everything, and we are using this provision, and we don't want to do it as an ATRIUM provision. And then this is how it looks completed. It's a beautiful space. And we actually did a simple analysis of this. It's not quite an ATRIUM, but we would demonstrated that if the fire starts, then the smoke will be collected in the space, and the smoke fan will take out some of it as well. But it was not designed to a full ATRIUM standard. And we were able to get this approved and through the jurisdiction again. Here's another interesting one. This is type 3A. We talked about the exterior wall requirements to be non-combustible, fire retardant treated. The problem with fire retardant treated is still that what happens in fire retardant treated wood is that it has chemicals inside. It reduces the structural capacity of the wood, and it becomes very difficult to work and expensive. So we actually have a white paper that we have submitted where instead of the fiberglass wood, we give a mineral wool combination with normal pieces, and we have an engineered system that will allow you to use standard wood framing in type 3B exterior wood with the mineral wool combination without using fire retardant treated wood. And really what happens is in a fire scenario, the individual 2x4 or 2x6 framing that is in the wall gets exposed from all three sides once the gypsum is compromised, because the fiberglass does not provide any resistance to heat at that temperature. But mineral wool stays in place, and the stud is exposed only at the edge. And the result of that actually is that the standard stud with rock wool insulation outperforms the fire retardant treated work meeting within the prescriptive. So in this one, we actually got far superior. It's T plus 70. Since the fire, 70 minutes was what the fire retardant treated wood worked, and 112 minutes is what the standard wood worked. So we actually got better fire resistance, better health performance, and better structural performance by doing an alternate. Here, this is an example of CLT that we have done. And I told you about the type 4B is the most difficult one, right? So one of the things in this one is this building it's 8 stories building. So it would be less than what is permitted in the type 4C construction type, but it is taller, and therefore it exceeds the 85 feet. It's about 105 or 110 feet tall. So this is significantly taller than what is permitted in type 4C. So the city said we want it to be type 4B construction. The client wanted the ceiling to be all exposed wood and the beams. The exterior walls were non-combustible, the interior columns were non-combustible, so there's a combination of concrete and wood building. And this is important to do. When you do CLT, sometimes people overdo wood. In our experience, it's a combination of wood and some other element like concrete or even gypsum that contrast adds value. And if you have everything in wood versus a combination of 2 surfaces, 2 elements, it actually a stronger visual element is my perspective. Of course, aesthetics in the eye of the beholder. So in this instance, the beams were spaced at 12 feet on center, and the glue lamp beams were almost 36 inches deep. So that is what made the floor to floor almost 15 stories. And that's what put the building taller than the standard wood frame building. Compared to that, we had done a Katerra project where the Katerra used joist at every 4 to 6 foot on center. So it almost made like a ribbed floor versus a post beam and post type of system. And so they are able to keep their floor to floor lower compared to the standard glue lamp. But the visual look of a glue lamp is very different. So I understand why the architect wanted to do this. So in this one, we actually are still developing that, but we actually compared the type 4B, type 4C, the actual full-scale testing that was done, that was part of the 2021 approval, final approval. So we're looking at all those data and generating in it, and we're demonstrating that there is very little difference between type 4B and type 4C, and that this building therefore should be permitted to have full exposed wood ceiling. And we are confident that we'll be able to demonstrate that and get it done. It's a couple of months away before we get all that done and approved, but that's where we're heading towards. I'll just close with some of the mass timber buildings that we work with, and then we have a few minutes still left for any open questions specific to this presentation or unrelated. I'm fine with questions even outside of this presentation. So this is the First Tech Credit Union, one of the largest in early mass timber buildings. This went through a big learning curve. We were brought in after the fact, the design was done, and the jurisdiction was really putting their hair out about how to get it approved, and we were brought in. So the core thing in this one was the communication to the jurisdiction. So we were able to communicate clearly how mass timber works. We were able to give specific details, and we did a lot of engineering judgments for each conditions and worked it. Again, see the contrast with wood and other materials, a combination seems to work well. In this particular building, they actually had one type of finish on the ceiling and other type of finish they used on the columns. And even that variation in the stands and the finish of the wood was enough to not make it too bland and actually add value to it. So think about that. Here's the Katerra building that we used the ribbed floor system as a building. This was a large university campus. They started out with a large atrium and then eliminated the atrium for cost reasons, kept it simple, and kept moving about it. This is a smaller building, Memorial, Meyer Memorial Trust, lever architecture. Lever architecture has been at the forefront of CLT throughout the country and here locally. In this one, this was not so much the entire building was CLT. The building was classified as a type 3B rather than type 4 building. There's some benefits to type 3 in a smaller building versus going to type 4C because the requirements are different. So at smaller scale, CLT may not be an advantage as a construction type. You want to use it as a material and the construction element and add value that way. Here's OSU Cascades, is a high-rise building, not high-rise, but tall building under high-rise provisions and multi-story, beautiful building, beautiful campus. And here they wanted to have multiple openings between the building and not have fire rate separation. Again, we worked with the architect to develop a performance analysis, went to the jurisdiction, demonstrated how it worked, and got it all approved. But the common misconception we still struggle with, and people think, oh, there's buildings that have open exit access stairs that were done in the early parts of 2012, and they can, oh, but somebody else did it, so we should be able to do it now. And just because somebody did it because the jurisdiction did not understand the code does not make it so that you can now keep doing it. So, but we were able to get them there by providing an alternate method that actually provided a sound scientific basis for what they were doing. And it's much safer for you as an architect to have that demonstrated rather than somewhere down the road have an accident, somebody come back and said, Mr. Architect or Miss Architect, you failed us and you didn't provide the due diligence and the professional level of competence that is expected of you. Here's the OSU Peavy Hall, one of the earliest buildings. Michael Green Architect was part of that. This is a very small structure. This is also the lab, the wood lab that Oregon State is developing as Tall Woods building. And it's exciting building. Again, had an atrium early on, was removed as small buildings and atrium struggle with the cost models, but it was a beautiful building to work with. This is the side yard by Skylab. This was also a fun building to do. Skylab is also an avant-garde architecture firm, pushes the limit, and we were able to work with them on that. So that's my presentation for today. Here's a list of services. We provide really a one-stop shop. Whatever you need to do, we can do that. So if you have a question, give us a call. We can help you. Sounds good. So I will now stop sharing so we can open it up. And Tim?
Yeah, that sounds great, Samir. And thanks again to Code Unlimited. We do have a question that we'll get to. First of all, I can't believe you said the architect didn't listen to us, of course, as if that's a regular occurrence.
I'll tell you, there are instances where we go in and architects saying, hey, I want to do this. I know I'll follow the rules. I said, have you ever followed the rules before? Why would this be different?
Yeah.
Let's work with what we got and get you the best answer.
Yeah. Well, with all your knowledge and insight and ability to model these things and come up with alternatives, I can't believe they wouldn't answer or wouldn't listen to you. So I do want to give our attendees instructions on how to get this learning unit recorded for HSW on your transcript. So what you'll want to do at this point, as soon as you're ready to do it, is use the chat function and enter your member number, and your chat may already be open, or you can click that option on the bottom of your screen to open up the chat. So put your member number in that chat function, and it will appear on the right-hand side, and Megan will be able to record those for you and make sure that that gets on your transcript. And we did have a question when you were talking about the connection points. So it related to the residual cross-section for load capacity assumes the resilience of wood after fire. How do you calculate joints for the same scenario?
Very similarly. So what we do is we look at the joint as part of that structural capacity and add on top of it. So if it was an intumescent, then we would take the minimum thickness of the steel that is there and develop an intumescent coating that goes on top of that. And it's a little different because most commonly the intumescents are developed for a thick structure. These are smaller, thinner plates, so we have to extrapolate from that. And the intumescent prevents the steel from reaching that temperature. If we do it with a wood calculator, then what we do is similarly assumes the excessive wood will be the one that will compromise and not be good to the steel until that point. Very similar to the beam construction, but just have to understand the steel member when you're doing intumescent and overlap wood.
Okay. And an additional question was if you could speak to the code allowable floor area of the upcoming type 4A, B, or C construction type. So would that be applicable to larger horizontal buildings like exhibition halls or transport facilities?
Yes, so typically the type 4B is almost like a type 1A. So type 4A is almost like a type 1A, type 4B is almost like a 1B construction, and type 4C is in between 1B and 3A. So your allowable area goes up. So if you're building like a large exhibition hall or transportation facility, if you have an unlimited area provision based on your separation and things like that, then you could do that. But if you don't have it, very likely in that scenario, you're probably wanting to do a type 4A building, but you would want your wood to be exposed at the ceiling. We are doing a similar condition in the Portland Airport expansion, for example, where their airports have very tall volumes and large volumes. And so we can, the building is actually not a type 4 construction, it's a type 1B construction, and they wanted to use wood in the roof of that building. And it's still in the process, so it's not finished yet. But in that one, again, what we do is do a fire analysis and demonstrate that in the worst case design fire condition, the temperature at the wood will not ignite the wood or would not burn it too much, whatever the criteria is, and that means of egress is maintained and the structural integrity is maintained. So if you're going to do that, very likely you'll come back and say, yes, but I want to keep the wood exposed, and we'll work with you.
Yeah. And what about, so Colorado's different from other states where they might have a statewide building code. Some of the codes, there are some minimums that are specified statewide, but for the most part, local jurisdictions have the authority to set their codes. So some of these upcoming code changes may not have caught up to the local jurisdictions adopting them. If you had a client or a design team that wanted to use something that's in these more recent codes, is it easy for them to do so and for that local jurisdiction to see them as in excess of an earlier code that they have and in compliance?
Not necessarily excess, but more current knowledge is how they see it. And depends on the jurisdiction and their comfort level. Some jurisdictions will allow you to swap up a code with just you talking to the jurisdiction. I want to use 2018, and today you're adopted 2015. The 2018 is consensus code, right? So that's the other part of the published code. It's a consensus code. It's gone through a rigorous review. So the jurisdiction does not know. Versus if you use a standard that was a separate standard or performance analysis, then the jurisdiction actually get concerned that, oh, do I have the knowledge or ability to review this level of technical presentation, right? So if it's already in the code, then there is comfort. They can also go to the ICC and ask questions. The prescriptive process would be that you would do an alternate materials method to adopt that portion of the code as part of your design process.
Okay, very good. One more housekeeping note before we continue the dialogue just a bit more. If you're still looking to enter your member number, go on the bottom of your Zoom window and look for the chat function. Click on that, and it should bring up the sidebar where you can enter your number at the bottom of that right-hand sidebar. We also will have this available as a recording, so if you wanted to take notes and may have missed something along the way and revisit a detail from this presentation, you'll be able to access that on our website. And then just one thing I noticed, two things that were really complimentary. One is that just an acknowledgement that many materials perform differently. They're not better or worse. And I've often seen fire officials say you can't use X because it's combustible. In a lot of cases, you know, that X is wood. Everything is subject to high temperature and egress and smoke.
Right.
So it's important to highlight that things perform differently. They're not good, bad, excusable, inexcusable, allowable, non-allowable. You just have to factor it in.
Right, exactly. And that's what we do. We go into the depths of what the code intent is and how the code actually performs, providing safety or not providing adequate safety. And when you kind of parse through all the complications, sometimes the jurisdiction come on and said, I've seen a building burn down. Yeah, but what was the cause, right? So we get down to the very core issues and demonstrate apples to apples.
Yeah, well, the Greenfield Tower, for example, you know, a layman's perspective might say, well, it had aluminum cladding, so that's a non-combustible material, right? Yeah, it's how it's assembled and how the air moves through it and how the thing starts in the first place.
And the European codes are different too. They don't work like American codes as well. So they have compartmentalization. Their exit systems are different. They didn't have sprinklers in their building. So there was a lot of other things that people don't even think about. They just focus on that one exterior element or material of the exterior cladding, but there are other factors that also made it what it did, what did happen.
Well, that wraps up our questions, and thanks again. Round of applause remotely from all of our attendees. Samir, great job. Code Unlimited. Appreciate all your work and beautiful stuff happening out in the Pacific Northwest. We're hoping to see more of that here in Denver and in the rest of the state of Colorado. We're a little further from those great forests, though, for those materials.
Right. Yeah,
thanks.
No, but I think that will happen in Colorado too. And thank you very much for the opportunity. And as you can see, I'm a master's in architecture from the University of Oregon, so I went over to the dark side, if you may. But I still feel like I'm very much designing. I'm designing with materials. I'm designing with words rather than lines, and participate in a lot of cool projects. So we're happy to work with any of your members if they have a question or two afterwards as well.
Very good. Well, appreciate it. And for those looking forward to our future conversations, we'll be up again next Wednesday. We're hosting a panel with AI Colorado firm principals from small firms. And the Wednesday following that, 2 weeks from today, will be a panel with AI Colorado firm principals representing large firms. And then we're also going to start doing more sessions on Tuesdays. So Tuesdays will be additional HSW credits. Next Tuesday, our next opportunity for folks to get some learning units will be an HSW session on kitchen specifications for aging in place. And then the Tuesday following that, we'll have some financial advice and projections on the economic market from Doug Parker with Design Business Advisors. So hope to see you again in the virtual space, and have a great week. Thanks.